Hello everyone, I'm sure you are doing extremely awesome. This video is kind of a finale of our six-part OS internal series that we have initially started around like couple of months back. So here we are going to understand how OS handles network requests. So it is very important aspects of operating system, and it is a very important aspect of the application engineer as well. So the way we are going to cover is, suppose we are an application engineer who is practically covering, once again, yeah. So suppose you are an application engineer who is ideally covering all the uh, application development of a given ecosystem, of a given technology ecosystem. Now our responsibility comes around the networking part. So when you are interacting with multiple cloud providers or some other external services from your hosted operating system, then it becomes very important to understand all the internals of the network stack, as well as how operating system interacts with other cloud services, other networking systems. So whether you are a front end or a backend developer, at the end of the day, we all are making network calls or some interactions with some other components. And that is where this knowledge will come very handy to us. So, moreover, we are going to cover a number of real life problems in cloud, how networking stack works under the hood when multiple hosted machine they talk among each other. So like we will see various codes like some Python code, Java code, or C sharp code, and we will try to see what exactly the basic principle based upon which this interaction among the networked elements are being tied upon. Okay, so as this is a as this is a networking internals and the plus operating system video, so let's start with, yeah, so let's start with the OSI layer. Okay, so when we are talking about the OSI layer, it is open system interaction, open system interconnection, and it refers to a conceptual model that characterizes and standardizes the communication between the computing systems. So suppose if there are two computing systems are there, suppose this is one CPU and this is one CPU, how both of them will talk among each other, like how this is going to send some kind of a request to this, and this is going to send some kind of a response to it. So how this request response among these two machines, like suppose this is M1 and this is M2, these two machines are going to happen, that is ideally being specified as a standard, and that standard is known as the OSI standards, and OSI has seven major layer around it. So what are the seven major layers? So first of all, like when we have our machine, it is connected with some kind of a router, right? So before it sends the it sends any kind of request, it is connected to some kind of a router via the wires. So what happens in that case is, like, the first step happens is basically the transmissions of the raw bits over the medium. So in that case, the machine A, suppose like M2 is making the request to M1. So let's make this M2, this M1. It will be easier for us to understand because we are sending the request from here. Okay, so uh, this from this machine M1, the user opens a browser and types a URL, and the browser prepares a HTTP request, right? So suppose as a step one, we come to the browser and some HTTPS URL we are typing, okay? And in machine M2, we are having a web server. Suppose I am just going into something like a reddit.com. Okay, so from here I come and I put something like reddit.com over here, and machine B from the web server receives the request and it will prepare the HTTP response for that. So let's see what happens one by one in this case. Okay, so machine f- th- from the M1 perspective, this is the first thing that happens. Like in the HTTPS URL, it is going to hit. Okay, so then what is going to happen is then it is going to encrypt that request. So whatever the request we are going to send, that is going to get encrypted. Okay, and who is responsible for encrypting it? Not only encrypted, also the format as well. So who is responsible for encrypting it at the very base level? So for that, our presentation layer is involved. So in the browser, when we do this, here come the physical layer, and here comes the presentation layer. Okay, now a session is being established. So till now no connection has been established. Okay, so now only this session will be established from M1 to M2. So in when this session is being established, that is the layer 5 or the session layer. So session establishment happens. So this is session layer. After that, the data which we are going to send, what will happen is this particular data, suppose this this is my data. Okay, so this data gets divided into multiple chunks. This data will not be like sending as a raw data, right? So it will get divided as a multiple chunks. So what would happen is a session is established on this session layer, and after that data is broken into segments, and TCP also adds the port number. Port number means, suppose this particular M2 in this web server, suppose I might have 3 web server hosted in the same machine. So suppose I am just going to web server 1. So after this session management layer, what would happen over here is data broken into segment, and TCP adds the port numbers of the target. Okay, so I hope it is clear till this point. So now we are standing on the layer 4, and this is being known as the transport layer as well. Okay, this is very important, the L4 and the L7. We will gradually, when we go ahead in this discussion, we will just see how important it is to understand the detailing around the uh, the layer 7, that is the application layer, and this layer 4, that is the transport layer. Okay, now after that it adds the source and the destination address. Source and destination, because till now it doesn't know where it has to go. So the source and the destination address will be added, and this happens in the network layer. Okay, and then what happens is it adds the MAC address. Okay, so MAC address means the machine identifiable address, right? So now what is the difference between the IP and the MAC address, that you might be thinking? Okay, so MAC address is basically the media access control address, and it is a unique identifier assigned to a network interface controller. So every machine has a given NIC card. Okay, so this also has a NIC card, M1, and this M2 also have a NIC card. So this network interface controller's address is being known as the MAC address. So what it does is it identifies the devices within a local network. Suppose I am sending it to a given local network, I am sending a request. Okay, and here I must mention that here IP is being added, that is the internet protocol address. Okay, so this IP, it uniquely identifies the device on the network, and what the MAC address does is the MAC address identify the network card of that particular of that particular network. Okay, so it operates on the data link layer level. So this is basically the data link layer. So to understand the difference between the IP and the MAC address, we also should appreciate one of the fact that when this request goes from M1 to M2, it goes through various hops around the network. Like for example, when we are sending a certain data from, suppose some of the US server from India, it doesn't directly hit the routing network of the US server. Rather, it goes through various hops around the world and then it reaches into the US. So, how both IP and MAC work together is, suppose our browser uses some kind of a domain name like this reddit.com. Okay, and then it is being resolved via DNS, and it gets an IP address like where exactly I need to send this particular message into. Okay, so that is the destination IP address, and also there is a destination MAC address as well. This is for the local delivery. So what happens is your router received it using the MAC address, then routes it based on the IP address. So at each level the MAC address can change. Okay, so at this level the MAC address can be MAC1, and at the next level what happens is the MAC address keep on changing, but the IP will always remain that IP1 that I am trying to see, I'm trying to send. Okay, so sorry, this will be IP1. So again, the destination IP address for the routing, it never changes, but when we go through various hops around the network. Okay, so let's understand this thing using the actual example. Suppose this is my IP. From there, I am trying to reach into the example.com. Okay, or the reddit.com. So reddit.com has certain IP address like 93.184.216.34. Okay, just a made up number. And what exactly happens over here is this has a default gateway as well. So it never directly being sent from this source IP. This is my source and this is my destination, right? It never directly being sent from the source to destination. It will go via various hops. So how it builds is it sends the packet to the default gateway. Okay, and there is a source MAC and then there is also a router MAC. So what is being determined is using ARP. Okay, so using address resolution protocol, it is being determined key what exactly is going to be my next MAC address hop. So this is going to be the address of my next hop. So ARP takes input of this destination IP, and what it determines is it determines what is going to be my next MAC address or my next hop. Okay, now to get the router's MAC and this point we understand, right? To get the router's MAC we use this thing called ARP. Now again, when router receives the packet, it looks again for the destination IP and it checks its routing table, and it find that the next hop is the next router. Suppose the first router hop was something like 192.16.0.0. Okay, so the next hop again it determines is something like 10.0.0.2. Okay, so in this way, this is the Next, hops MAC address we keep on getting in this way gradually, but in this process our source IP and our destination IP always remain same, and this thing is being handled using the MAC address. And as you probably understand now why MAC address is important and what is the role of a data link layer. So after data link layer, what happens is it convert the data into at the one, it converts the data into electrical signals. Okay, it converts the data into electrical, or if it is optical fiber, there will be optical signals, and send it over by cable or Wi-Fi. Okay, so this is the role of the physical layer. Now, if we see this thing carefully, how M2 will start resolving it is completely on the opposite direction. So till now, things have gone from this to this. Like we have come from this first level of browser to this level of uh, from application layer where the browser resides to this level of the physical layer. Okay, now it happens on the other way around, like while we start resolving it. So how M2 does it? For M2 it is completely on the other way around. How it is, let's discuss. Okay, so at first uh, the M2 will receive the signals and convert them back into bits. Okay, so then I will just write it from 7 to 1. How it does the whole thing. It receives the signal and convert to bits. Okay, then at the data link layer, it uses MAC to deliver data to correct device. Okay, so it keep on taking the data from one hop to another. Now at next level, what would happen is it uses the IP to route the data to correct machine. Okay, so this MAC probably comes into the router level, and then what happens is using IP it goes to the exact machine, and then session established, as you can, sorry, it will be the 4. No, before session established it will be our transport layer. So what it will do is it will reassemble all the segments and check for errors, and then it will come to the session establishment, and after establishing the session it probably deserialize or decodes the data. This at presentation layer, what happened is like encoding plus format plus with I can write also the encoding as well. So it decodes the data, and then what happens is after decoding it, web server receives and processes the data. Web server prepares, processes and prepare the data. Okay, so you see here what exactly is happening here is here from the browser to the physical layer I'm coming, and during M2 from the physical layer to the browser I'm coming, and once again once it is like ready with the response, it will again go through the whole cycle and it will keep on sending the data to the from M1 the data will come to M2. Like once it prepare the data, again in this whole process it will come, and in this whole process it will be decoded at the M1 side. So probably you understand, like this is quite an expensive process, although it happens within like in our eyes in a millisecond, or in a second delay. Like the moment we are hitting something, we are getting it from the website. But a lot of thing happens. There is a whole stack of segments that this particular request has to go through and has to come back. So um, one very big mistake I did, like when I was just going through it, it should be application layer instead of physical layer. So it comes like this from the. I hope you are getting the idea, like how the data is flowing. So just please excuse my few of the misnomer that I did while typing. But anyway, let's take a complete look again, because this is probably one of the most important concept in terms of the computer science networking. So we will just revisit it once again or revise it one more time. So when it comes to the physical layer, what exactly happening there is, when it comes to physical layer, it basically defines the voltage, like how do we send something like a 1 or 0. Okay, so 1 can be 5 volt and 0 can be 0 volt, and some timings are there, right? So using fiber optics or Wi-Fi signals, we are we are sending that data from the physical layer to the next layer. And then it comes to the data link layer. In data link layer, what happens is the MAC address gets added there. So the MAC address is basically to and from, like from which uh, source to which destination MAC address we are going, that will be defined over here. Okay, so here the MAC address are being added. Then the next layer come as a network layer. So here we add the actual IP address where we want to go. So here the source and destination IP address. And why source IP address is important? Because when I reach to the destination, it need to know where exactly the data it needs to send back. That is why the source IP is also important. So source and destination IP address, it gets added over here, and this thing is being encapsulated. It's called something as segment or header. Sorry, IP headers. Segment will come into the next level. Then it comes into the transport layer. Again, one of the most important layer. It determines which app would receive the data in the host machine. So the idea is, like, a particular host machine can have multiple web servers, right? So which exact web server that I am redirecting it to. Suppose some web server is hosted in 8080, someone is hosted in 8081. Suppose I want to target the 8081 hosted application. So in that case, the whatever the information that we added, the TCP or the UDP header plus the packet payload, that becomes very important in terms of the whole communication. Then the long-lived conversation or the actual session is being established into the session layer, that is the layer 5. Okay, so here something called TLS or transport layer security is being imposed, and it can be TLS or it can be like the other protocols as well, like for example the WebSocket, gRPC. All this sessions are being mentioned and maintained using the session layer. So it manages the stateful interaction between the endpoints. Suppose I need to create and establish a session for some time, so session layer would come in play on that particular part. And now how exactly we are going to interpret that data, with a got that data, right? Like from the physical layer, data link, network transport and session through which the session is being established. So now we already got that data into our network. So after that, this presentation layer determines how do we interpret this data. So it is going to encode, decode, or suppose if it is a zip format, it is going to unzip, or if it is a MP4 format, how it is going to use that. So it ensures that data is in usable format. Okay, and then it comes to the last layer, that is the application layer. So how do user interact with the network? Before going to that application layer, let's understand one of the intuitive part of the presentation layer. So now probably you understand that this is here when the session is established, right? So now that means we are in the host machine. We are in the host machine. So presentation layer or the layer 6 of this OSI model exists within the same host machine as a part of the software stack, and it is not really a some different physical device or something. So over here what happens is, in presentation layer encode or decodes whatever the data stream that we got, and then and the application layer, when it comes, the application layer is basically like the nothing but the browser. So when it comes to the application layer, here web browser, or not only the browser, suppose you have some kind of a app like a desktop app of Netflix. Okay, suppose you have this Netflix desktop app, or some kind of a API interaction you are doing via any kind of the clients like Postman. So all these things are happening at the end, like when we see that data is in a given format, that happens in the application level. So I hope now it starts making sense to you that what exactly is happening over here. So there is application layer. From the application layer, the request is being sent. Request stream start, and then it goes basically presentation layer. It gets decoded. It gets decoded and being passed on to the next layer, that is the session layer. Decoded and passed on to the session layer, and then session layer creates the actual session using transport, network, data link, and physical layer. And after that, when the data comes, the similar thing happens. So these three things you can see, it is happening onto the host side, and this happen is on a external networking side. This way we can try to understand the whole layer by layer breakdown and their how exactly they are interacting with the rest of the stack. Okay, so now when we are talking about this theory, let's let's acknowledge one fact, that this theory, although it sounds quite good, in real life networking, I want to make this fact in a bold point to you. Okay, in real life networking, the line between each layer blurs like anything. Okay, so why is it so? We will also try to take one example and see. So suppose take an example of Netflix. Okay, what happens in the Netflix is sending some video over the wire, right? Does it go through all these steps? The answer is no. Okay, so what Netflix does is it bypass the strict layer. It bypass the strict layers for what reason? For performance. Okay, so what they behind the scene does is, instead of the age old TCP, they use something called a QUIC, or custom UDP based system to allow application logic to directly influence to the transport layer. So the thing that happening is, like, we were thinking of this many layers are going, and then we are going into the transport layer, right? So here what happens is, application layer can directly talks to the transport layer. So here you can see, like, I will just write the text over here. Application, it skips the presentation session and injects directly into the transport by using UDP protocol. And UDP handles the transport, and then it continues down to the network, link, and physical. So from here, what happens is, from transport, we then go to things like the other part of the system, like the network, data link, and of course the physical. So, so the point that I'm trying to make is, although we are studying all this thing religiously to just understand how exactly OSI layer works, but when it comes to the real life implementation, many thing changes over there. Now, why this kind of optimization Netflix does? So because Netflix doesn't really require any direct session management, and neither it requires any kind of encoding decoding at the presentation layer, and it also require some kind of a, like a it requires a real-time streaming. And instead of creating all those formal connections like we did over there, it has to prioritize its speed, because that is the need of the hour for any kind of streaming platform. So if anybody asks you, like, why Netflix adopted this, the first thing is that it doesn't require any kind of session management. Second is, no encryption is required for it. Third is, it requires speed over reliability. And also, like, TCP gives us a lot of things like retransmission and other facilities which it doesn't need. It doesn't require retransmission if a packet fails. So just think it more organically. When we are trying to send a chunk of video, if that video, I mean, gets distorted for a second or so, that means that particular packet might not have arrived there. So we see some sort of a distortion at that particular time, and then again the video revives, right? So is it really required to send that transmission or send that packet again? The answer is no. In this perspective, one of the more important thing we must mention about the UDP is, UDP is nothing but user datagram protocol, and it is a connectionless and unreliable. Okay, so let's acknowledge this, like UDP is connectionless and unreliable. And guys, we will cover UDP in much more detail in our networking series. So right now, just understand this: for TCP, we create the complete connection with a handshake, with a session, with the encryption, whatnot. But for UDP, we do not need all these things. Okay, so this is a communication protocol that permits data to be sent without establishing a connection or even ensuring the delivery of, that is what the reliability is, right? And it emphasizes low latency and reduce overhead. So that is the primary USP of UDP. And also it doesn't have any flow control or other things like the congestion control, all mechanisms like that. And again, the difference between the TCP, UDP and QUIC, all these things probably we will cover in very detail in our networking series. For the time being, just know about this thing, that OSI layer is there, but it is not a strict layer that all the modern application follows. There are at times when we bypass few of the layers to just speed up our processes, and how we can do that is various OS tweakings, which we will again take a look into that. But as we just started discussing around this TCP and the UDP, so probably we understand probably we understand one thing, that maintaining s- when maintaining state is no longer required, at that time we can use what? We can skip the layers, because this layers basically enforces security, state and whatnot. But in case we do not need it, we can skip them. Okay, we can skip the layers. So just take a example of any bank. Suppose there is Bank of America. Okay, suppose Bank of America is maintaining their own transaction system. So is in this case, is state required? The answer is yes, the state is required. Is reliability required? The answer is yes, it is required. Is security required? Again, the answer is yes. All the encryptions and everything is being required. So in this case, the like the most go-to option is we have to go through the whole OSI layer and the TCP connection, or the transmission control protocol that we can use over here. And TCP uses things like sequence numbers, session token, auth state, and things like congestion control, order control. All these things that are in that in a TCP connection can be achieved. In that case, the Bank of America can utilize all of them and design their system. Now, when we are talking about a live video streaming, suppose you are designing a any like your startup where you are doing a live video streaming of some cooking competition. Okay, so during your live video streaming, is what is the most important thing? The most important thing is not the state management. Okay, the most important thing is the speed or the latency in which data is to be transferred. Now, why state is like why state is rather a problem here, because maintaining a state like where the TCP handshake or the other sequencing everything is happening, that will invariably introduce a delay over there. So that is why in a things like live video streaming, we do not need to go via all the layers. So what we can do is, in this case, we can use UDP connection or even QUIC. Okay, so like it is faster, it is it is definitely faster. And from the operating system perspective, because we do not need to handle all these things like the sequence number, session token, and the congestions. So in that case, what happens is it is very less memory consuming as well. So suppose let's take a real life use case. Like Amazon sees that there is an increase in latency in its order processing. So how we are going to diagnose it in a layer by layer manner? So when I talk about this use case, let's talk about this. So Amazon e-commerce. sees a sudden latency increase during order processing. So how this knowledge of, now the question is how this knowledge of OSI plus networking is going to help us to investigate this issue. Okay, so let's go one by one in each layer and let's see what is happening and how we can see how we can see what is the root cause of this particular issue. Let's start from layer 7. Okay, so what happens is like user report the increased latency, and what we are going to do is we are going to check the application log. And here when we say we are going to check application log, that means we are going to see whether our application processing like db call and how we do the logic process, whether that is taking time or not. Okay, so that should be our first point of latency investigation. That should be our first point, and whether all the services like the microservices and any interactions, all the application level interactions are happening within agreed time. Okay, so that will be our first analysis, and this will happen on the layer 7, that is in the application layer. So after that application layer we would come to the layer 6, that is the presentation layer. Now we need to understand whether the encryption that is happening around it. So like we are this presentation layer, what it does is it encrypts the data, right? And any protocol specific transformation it does. So we need to understand, so any compression or encryption related issue are happening or not, and this could be coupled with layer 7 only. How? In our application log only we can add whether the compression or the encryption is taking encryption decryption or the encoding decoding is taking some time or not, and based on that we could determine, okay, it is a layer 6 or a layer 7 problem. So what generally happens is in the first level, in the layer 7, if we detect any issue, we will go ahead and fix our application logic, suppose apply parallelism, apply some kind of other techniques which would reduce our latency. And in layer 6 if we face any issue, what we would do is we probably need to change our encoding or um, encryption model. Okay, so maybe the encryption library is taking too much time. Okay, so now there comes the layer 5, that is the session layer. So whether the session setup and the management appear normal or not. So here we are going to review the session related logs. So when a session is being established, is there anything odd that we are seeing at that level or not? Okay, so those are the things we would see at the session layer, and probably like most of the cases session layer would not be the culprit here. Session layer, it works kind of a seamlessly, it is being controlled by the OS. We will come into that point as well. Okay, just right after this investigation we will come into the operating system details. Okay, now it comes to the transport layer. So in transport layer, what we are going to see is the RTT time. So we are going to take two server and the layer 4 between two endpoints. What is the round trip time? Okay, And here what we can use is we can use tools like TCP dump, and we can use tools like Wireshark also to analyze the TCP packets. And we can we can have like multiple issues can happen there, like the slow acknowledgement, multiple transmissions or whatnot. So we are going to check TCP dump, Wireshark. So here things like delayed acknowledgement can happen. Okay, so we have to keep on looking into this. And then after this transport layer, the data will come to the layer 3. So again, in the layer 3 is basically the networking layer. So we are going to see the network paths. So to understand the network path, we are going to use something like, I think, trace route we can use. So for the trace route, what happens is uh, it gives you whether the packets are being routed within an optimized path or not. So this can be again if we are not taking the optimized path. So something like if we are not taking the optimized route, there could be increased latency. Okay, and then again it comes layer 2, that is a data link layer. So data link layer is responsible for core switching, and it is for the congestion control, etc. Right? The issues that might happen over here in layer 2 are really technical. Okay, so there could be too much traffic through a single port, there can be switch buffer fills up. Generally the application engineer would not look into this layer, but it is always good to know, like frequent MAC address movement between the ports. Things like VLAN misconfiguration can happen, even there are port flapping, or even some hardware failures can happen. So this can be a really sensitive layer in terms of the errors, and these are highly technical, but they are generally handled by the actual core network engineers. So where we could do the spanning tree, we could they would explore the MAC address table, they would explore the faulty cables and hardware and whatnot. Okay, so after that we will come into the physical layer, that is in the layer 1. So in the layer 1, we have to see whether the fiber links are working correctly or not, and if it is older version of the fiber links, can we get into a uh, more modern version, verify the cable integrity, the optical signal strength. Those are the things, probably like all the hardware indications we probably check in the layer 1. So you see, like the issue at the initial level might look very trivial, that we are seeing that there is a in there is an increased latency during the order processing. But when we just go deep into it, there can be issue in so many layers. And when we are having a distributed network at a scale of Amazon, anywhere down the anywhere down the place this error might happen. Okay, so now I think we understand and appreciate the fact that how this networking stack comes together and transmit the data from one layer to another, and how it is very imperative to understand from an application engineer perspective, that just to shrug off that in my application log I see everything is working fine, in my local there is no problem. Generally that is what the application engineer always respond. Alongside that, as a true engineer, we can also probe the other teams to think in this direction. We might not have direct access to what is happening in our transport layer, or what is happening in some of the network hops, but we can always direct them to go into the TCP dumps, go into the Wireshark, go into the trace route to understand the actual problem. Okay, so now we know how a full layer of network to be diagnosed using OSI concepts. Now let's take an example of a web server operating system. Now in this part of the video is going to be one of the most important concepts that in any part of our application development we will need, because this is where we are going to bridge the gap between the operating system and the networking. So suppose there is a client sitting like this. Okay, so this client is interacting with a host or a server machine like this. So initially what happens is, like, even before making this connection on a very high level, the browser will ask for the OS for the IP address of the particular host machine that it is trying to reach to. So suppose from the browser I am trying to go to the reddit.com. Okay, so it will do some kind of a DNS lookup, and from the DNS lookup, suppose it gets that there is a host which public IP address is something like 93.184.21.34. Okay, so now what happens is, in the very first step, browser will make a socket call. Okay, so browser will make a socket call, and what exactly this socket call will do is, this will open a connection with a unconnected state. So there is a socket call that is being made, and our socket is currently now in a unconnected state. Okay, so these are our two primary entities over there, this browser and this host server machine. So now that we are in this unconnected state, the first thing that the browser will do to create a TCP connection is, it will send a SYN signal. Okay, so SYN signal, it is nothing but this is the very first step on this. So this is this will be the very first step of our initiating the connection. Once this socket is being called, it is still in the unconnected state. Okay, so after it receives the connection, what we are going to get back is, a SYN ACK. So it is a acknowledgement of a SYN connection request that we have. So this is going to be our number 2. Okay, so the moment this SYN ACK we are getting, then what happens is, we make a statement that the connection is being established. So you see there are 3 steps that are happening. At first we are in an unconnected state, and then SYN ACK, and after that the connection or is being established, or connected state, our socket comes. So there is a 3-way handshake that is happening. That is why TCP is called a 3-way handshake. Okay, so here is a 3-way handshake that is happening over here. So now from here, the operating system kernel will come into play. Okay, so how would the kernel will play a part here? So suppose this client is nothing but an operating system, right? So this client kernel, what it will do is, it will send its data, or whatever the request that it want to send, it will send that request to a send buffer. Okay, so now this particular request will be put into a send buffer, and from the send buffer, so suppose uh, this part is completely on the operating system side only. Okay, so from the send buffer, where it will go is, it will go into the NIC card of it, although I'm writing it on in between, but it is initially on the same level. All right, it is initially on the same level of the operating system only. So from the operating system's NIC card, or the network interface card, what will happen is, it will go to the host machine network interface card. So here, through the whole OSI stack, this is very important to understand, that after this step, it goes through the whole OSI stack. The message that we are trying to send will go through the whole OSI stack. So here, suppose we are sending our request, it will go to send buffer to NIC to whole OSI stack. Anyway, I'm just putting it here for convenience. Okay, so it will go to the whole OSI stack and suppose just name it as the part 5, and from the OSI stack it will go and end up into the network interface card of the host machine. So from there what would happen is, from there again, the most important part in operating system, again for the networking, you know, the kernel. So the kernel will come in play, and what kernel will do is kernel will identify all this information like the IP, the source IP, the source port. it will it will keep track of all these things. Okay, and this will be my step number 6, like when from the NIC the kernel is being notified that there is a certain message that is sitting over here. This will be my number 6, and from there, so here one more thing, like a send signal is being created. So be be cognizant of all this signals as well. This is a socket signal and this is a send signal. Okay, so from this send signal, what would happen over here is another signal will be written after this, after the kernel, that is known as the write. Okay, so write is again another signal, and where it will come, it will come to the receive buffer. So probably you understand this thing now, that earlier we were in a send buffer over here, and over here we are in a receive buffer. So it will be writing into this, and this is going to be my step number 7. So from here the thing will come into the application specific space, or what we known as the user space as well. So from the receive buffer, now suppose there are multiple web servers are there, right, in the same host machine. Suppose there is web server 1, web server 2, web server 1, web server 2. I have sent for the web server 1. So now it will be in the application space of, or the, or we can tell it as a user space also. We can have it in a user space buffer, which is application specific. Okay, this is a application specific buffer, and from there it would process all the data. Okay, so here only the processing will happen, where suppose there is a application logic might run, there is a application logic might run over there. Okay, after the receive buffer, and from there once the response is being ready, so now I have my response ready, right? So once my response is being ready, again I will send this data to kernel. Okay, so it is the same kernel, it is the same kernel, I'm just copy pasting it in two places. Okay, and what kernel would do is kernel would have its own send buffer. Like here guys, probably we understand that there is this request is being put to this send buffer. Now I am sending the response back, so it comes to another send buffer. Okay, so from kernel I'm passing it to another send buffer, and then it is pretty much the same thing what happened over there. I am going to send, this is again going to go through the whole OSI stack, and where it will end up is, it will again end up in a similar manner. It will come to the NIC, and it will come to the network interface card, and from the network interface card it will again go to the kernel, and in the kernel where it will be placed, it will be placed in something called receive buffer. Something called receive buffer, and from the receive buffer, this browser that we have over there, again let me just copy paste it. This browser is going to fire up a command that is called as read, and then it will read the whole response. So now probably you understand just a simple request response when it goes around the internet, how much effort or how much things that comes in play. So let me just number few things real quick. Like this will be I have written this thing as number 6, so this is 7, this will be my 8, and this will be, after that, this will be my 9. Then my OSI stack, this is going to be 10. And placing data into the kernel is my number 11. And at last, when it goes over here, it is number 12. Of course, there are some other nuances also in this process. I'm not going into the details of it, but if you have understood those things, like if you haven't got any part, please rewind the video and try to see what exactly happening. Like the DNS resolution over here, it got the IP. Then probably you understand how the socket creation is happening from the client perspective. Then what exactly is happening for this three-way handshake. Then after that three-way handshake, uh, we have our TLS handshake as well, which I haven't really covered in detail over there, but the keys are being exchanged at that level. Okay, so when the TLS handshake happens, so after this connection established, one more thing that happened, like we can write as 3.2, 3.1, that is the TLS handshake. Okay, so the TLS handshake also happens. After TLS handshake, the HTTP request will be sent via NIC card, the whole OSI stack to the NIC of the host operating system, and from there the kernel determines the receive buffer and the receive buffer of the user space, or the where the application specific logic will run, and then the kernel copies the data into the send buffer, and then packets again go through the same network OSI stack, and in the server side, the packet, once the packet arrives, the NIC gets into an interrupt mode and the packet goes through the network, network stack, and kernel identifies, yeah, so here kernel again identifies that some message is sitting there in the NIC, and what happens is after that we send that to the receive buffer. Okay, and then web server, uh, like when we are sorry, the browser then read it from the receive buffer, and the whole process is being completed. So in this process there are few interesting comments that we have seen, like the socket. Then also there is, initially there will be something called a connect request, and then read and write. Okay, and also at the end, if we want to close this connection, this whole connection explicitly, then we send something called a close, which is also known as fin or finish. Okay, so if we send a call a fin flag, then it will be this connection will be finished. So now some this is the one that I wanted to cover, and few of the things I haven't intentionally covered is because that would have made this video like longer than anything. So there are things like system details of the system calls. Okay, so what are the system calls that has happened, and there are the file descriptors. File descriptor is nothing but it represents what are the open connections, and kernels generally read from those file descriptor only to understand what are the open connection and what are the data that are coming through that descriptor. It is basically the open connections. at the operating system end. And then one very important thing that is called TCB, or transmission control block. So for each of this connection, like we only the image might be looking a bit complicated, but the truth is we only have created a single connection here. So when there is a web server, there may be thousands or 10,000s or closely, I don't know how many connection would be there. So all these connections need to be state managed separately, right? So in that case, we need TCB. It is the, or the transmission control block, that is the holding state of each connection. Okay, and then there is also context switch, which I already covered, like when one by one the requests keep on coming, how exactly the operating system behaves, uh, what exactly happened for the interrupt, okay, and what exactly happened for the TCP congestion protocol. So these are the some of the details which I haven't gone into details, but they are more onto the networking side. So maybe the TCP congestion protocol and this transmission control block we might be covering while we complete our, while we will go through our go to our networking uh, video series. Okay, now that we understand the most important part, let's understand from the code perspective also. So we saw the whole, so how we are progressing exactly is we saw the whole OSI stack. Then we saw in real life what exactly happens is like OSI stack is not exactly the holy grail of truth. Then we came to understand that for the live video streaming or for Bank of America, how the different kind of a OSI stack the application or the data has to go through. Then we tried to explore a real life scenario where we try to probe into what exactly happened, like when suppose there is a simple latency problem, but we have gone through the all the details around it and all the layers to appreciate the fact that how every layer attributes to can attribute to some of the problem and some of the advantages around the whole OSI stack. And then it comes to the what is the role of operating system in this networking. So our next stage that we are going into is nothing but where we will try to cover few of our application specific coding. Okay, so suppose we are talking about things like our Python. Okay, so this is a particular Python code where we are calling a certain endpoint, and you can see like we are sending a certain data. Okay, there is another piece of code I am putting here. This is the C sharp code, and over here you can see we are again awaiting a certain response. In both the cases we are awaiting this certain response, we are getting the response results, and we are sending some kind of a JSON. Okay, and also suppose for Java, so this particular thing is for Java. So for Java you see in same way for the web client, using web client we are making this call, and we are passing this body value or the JSON towards that. Okay, so uh, what exactly happens from the operating system or from our code or from this libraries when we are making this kind of a call, like for example from a C sharp library I'm just making this await http client dot post async. What exactly happens there? Okay, so um, you can probably see here that before sending the data, what I am doing is I am using one encoding, and I am changing the data to like application.json. So what exactly is happening over here is, so the thing that is happening over here is we are serializing the data, and serialization of data happens in what level? So let me just take you through in a very organic way. So serialization of the JSON or the encoding that we are doing, it happens on the presentation layer. Okay, and then when we are creating a HTTP request, in which layer it works? It works on the layer 7 or the application layer. Okay, so this is the layer 7 or the application layer. It happens. Now when we are opening a connection, opening a TCP connection, so the moment we are writing this code of http client.post async, what happens is a connection will be opened. Okay, one connection will be opened, and there r- right before this section we discussed about connect call, right? So that connect call happens, and from which layer it is being fired? It is being fired from the transport layer or the layer 4. Okay, so it is transport layer or the layer 4. Now again, once we send the data, like all the NIC buffers, everything that comes in play, so what happens is from layer 4 to 3 to 1, it gets accepted uh, into the server, and in this point of time we will be wait for response. Okay, and the layer 4 only. So the layer 4 is the particular TCP connection which is generally waiting for the response, and then what happens is it blocks that particular socket but releases the thread. So this thing again we discussed in detail in one of our previous video in this series. So I hope as you are coming through the in a sequential manner, so you understand that fact that it releases the thread, but what it does is it blocks the socket so that it can receive the response. Okay, so once the OS buffers the response, then again, like from gradually from layer 4 to layer 7, the data comes, like the deserialization, the reading of the data, the HTTP response, everything. So again, at this level, so here we have uh, serialized the data, right? So the deserialization plus the actual HTTP response, everything we get in this manner. And there are few other things that happen mm, behind the scene which we should mention verbally. That is, the first thing is the runtime. Okay, so what the runtime does is it resolves the api.otherservices.com to an IP address, and then the HTTP client connection, the HTTP client connection pool checks for an existing and the warm connection, whether any existing connection is there or not. In that case, it uses that, and after that, when it actually sends the response, it initiates a TCP or a three-way handshake connection. It starts. Okay, SYN ACK and the ACK that we just saw there. Okay, and a TLS handshake also occurs inside this TCP connection, and then the segmentation, the serialized HTTP requests are broken into TCP segment, and each is given a sequence number, and each TCP segment is wrapped in an IP packet with the source and destination IP address, and it being sent, and each IP packet is again then wrapped into the Ethernet frame with the source and destination MAC address. So I'm not writing all those things in detail because we already kind of discussed it, but this is what exactly, like, although these codes are already given, most of the things are given by library, but the library behind the scene, they calls uh, this methods like connect, it reads from the buffer, it creates the socket connection, everything is being done by the libraries behind the scene. So that is why, like, understanding this concept is very important. Like if anything goes wrong in this process, then like it as an application developer, then only, like, if we know these concepts in detail, then only we'll be able to will be able to understand and diagnose it. So there are two more comment that I want to talk, that is called select and epoll. Okay, so what is select and epoll? So this is basically the IO multiplexing mechanism provided by OS. So they allow a program to monitor multiple socket and notified when a data is ready. So this is why select and epoll I mentioned. This is the core of the await. So this await that you see over here, okay, this await, or here also you see the await. So this select and epoll, using this, I will just write the thing so that it get imprinted in the memory. Program to monitor multiple sockets and be notified when data is ready to read and write without blocking any thread. So it basically releases the thread, and select and epoll will keep on polling that whether any response is being coming or not, and if it is any request is coming, it will say that you that we are ready to read or write, and similarly for the response. Okay, now why it is important in the high performant, in the async operations like httpx or the web client, we don't want to block a thread waiting for the data. Instead of, the app tells, like using select and poll, it tells, let me know when socket has the data. As simple as that. So what exactly happens is, app registers a socket with epoll when the connection is being created. Kernel watches the, so I will just write it, app registers the socket with epoll, and then kernel watches the state of that socket. So when a data arrives, on data arrival, interrupt is being sent, is sent, and then the socket will be marked as, readable, and then app is notified and read the data. This is on a very high level what happens. So in .NET, Python and Java, these are totally abstracted away, but under the hood, the async IO and the event loops totally rely on epoll or KQ or IOCP. Okay, so like epoll is basically for the Linux, and for Windows it is IOCP. So behind the scene, that is how the implementation is being done. All right. So here onwards, we are going to do some concept building exercises. So why this concept building exercises are necessary? Because oftentimes we find that some of the concepts are quite digestible while we are studying around it, but how exactly we should apply it into our real world problem statement, that becomes a problem. So few of the concept building exercises. So as a first one, let's take an example of that what exactly happened in a await call. Okay, so when a call is awaited, at what point, when a call is awaited, at what point the OSI model journey does the execution await. So like, is it like before the data is sent, or after response is received? So just pause the video and give yourself like a good time just to answer this. If you can answer this, probably you have actually understood how the await works, in the operating system and with the networking layer behind the scene. So the answer is await happens right after the request is hand off to the OS kernel to send. So during await, what happens is request is handed off to OS kernel to send it to OSI layer. Okay. And one more important thing is that the thread that was executing, the thread becomes free. So when the call is awaited, it is basically before the data is sent, and even before that, so when OS kernels are being actually handed over this responsibility to send the data to the OSI layer, like the way we covered in this particular diagram, right? There is a send buffer, then it comes to the NIC card, and in this way. So yeah, this is one of the example. Let's take another example. Okay, so suppose we are getting some kind of a timeout, like a task cancelled exception. So does it mean like the request, this one, task cancelled exception? So does this mean that the request never reached the server? And how could you design the system to be idempotent or to safely retry for this ambiguous situation? So first of all, please pause the video and try to answer this question. Okay, so the answer is no. It doesn't mean that request never reach this server. So task cancel can happen in multiple scenarios, right? Like there is a DNS failure from client end itself, okay, or some kind of a network down or network reachability problem issue again from the client end. Okay, request reach the server, but response got delayed, or whatever the timeout that we have set in the TCP timeout reaches. Okay, during this. So whenever we are getting this kind of a task cancelled exception, there can be multitude of things. So never ever uh, come into a direct conclusion while debugging your application or getting into any kind of or solving any kind of issue for the application where this thread is involved. Never come into a direct conclusion about the networking that something is not reachable or some part of the code is taking too much of a time. We have to go through the log very diligently to understand this. So the solution to this kind of problem is like we are going to do a retry, and I will leave it to your homework. So you just see how idempotent requests are being sent, and plus the retry with exponential backup are being done. Okay, so these are two very primary thing for the retry. So anytime we are getting a task cancelled exception, we can catch that and we can fire up a retry. But like in retry also, how much time we will give for each of the requests, so that we do not hit any rate limit or any other kind of issue. And also if my request is already under process, like request has reached the server but the processing is taking time, I do not want to create a duplicate request. Like for a financial system, if I if I'm not getting the response on a very first place, and if I just retry it and do another transaction, then you can see what kind of a catastrophic failure will happen. So idempotency comes in play in that point of time, and again it is a very important concept, not exactly in the scope of operating system and the networking discussion. I will leave it to your homework to understand this. Okay, so also, there are a couple of bad practices that I want to bring it to your attention during as an application engineer, why we are writing code and why we are covering this, because because like this OS internals are mostly for the application engineers and the SREs. So uh, you can see over here, whenever we are trying to create a user, uh, we are doing something like a every time we are creating a new HTTP client. All right. So whenever we are creating new HTTP client, what happens behind the scene? The first thing happens is a new TCP socket is created. Okay. So, and after the request, because it is being wrapped in a using block, socket closed. Okay. Or the socket enters the time wait state. Now, what would happen under heavy load? So, under heavy load, when I say heavy load means like when probably tens of thousands of requests are coming at the same time of creating a user. Suppose a lot of people are signing up for our services. Okay, so what would happen? Thousands of short-lived connections are created there. Okay, and OS will run out of the ephemeral port that used for the outgoing connections, right? Because for sending every connection or for sending every results, we also need to get my port opened up, and new connection will fail into the error like the socket exception or task cancelled exception. So what is the remediation of that? So for that, we basically create a singleton sort of a pattern. We are going to create like a common HTTP client for accessing the web. For example, something like this. For example, something like this we are going to do. We are going to inject it here, and in all of our service calls we are going to use it. Or also what we can do is we can do a singleton sort of a thing, that or a lazy initializer, that if it is if the connection is not there, then only create a new one. Okay, so we have to be very cautious while writing our network connection code, because as you can see, this many number of like every time I create a new request, this many number of things happens behind the scene, like the sin sek, and then the full connection is being established with the TLS establishment, and the other stuff like the termination fin, everything comes in play. So be very cautious and very frugal while creating this kind of connection, this kind of HTTP client connection or the TCP connections. So now, now we understand a few of the real life scenarios, and we also have got some idea of the code, how we are going to interact with the network through our code, be it in Python, C Sharp, Java, Rust, Scala, any language you take. Behind the scene, this is the basic principle that happens. Now, let's talk about our cloud infrastructure. Okay, in our cloud infra, why this operating system and the um, networking concepts are important. So when we are talking about things like EC2, just understand these things. EC2 is nothing but a full OS with a networking stack. So if you are having your single machine, so EC2 or Azure VM, they are nothing but full OS with networking stack. So the moment you are spinning up EC2 or Azure VM, be very cautious that you have to build your whole networking stack end to end there. Okay, so you are not going to get uh, of course you are going to get some of the managed platforms there, like the security groups, some built-in security groups you will get, things like access control list, ACLs you are going to get, but the creating of the socket, bind, listen, managing the ephemeral port, all you have to do by yourself. So that becomes how EC2 or the Azure VM this machines comes in play. And when it comes onto the ECS or a EKS, like when it comes to the containerization, in case you are not very much um, well versed with the containerization, just understand that in a single host machine there will be multiple container application will be staying. So what happens there is something called a shared kernel that is being used, and shared kernel with all the instances will have a isolated namespace on top of that shared kernel. Okay, so containers there share the host OS kernel. So it looks something like this. So suppose this is my host machine, okay, and in my host machine I am having this container 1, container 2, something like this. I'm not overcomplicating it. For the time being, I'm only creating this container 1 and container 2. And what happens over there is each container, this is the host is also being called as pod. So within the pod, each container will have their own loopback interface, will have their own routing tables, and a shared OS kernel. So if we have to just now think about all the TCP IP stack or the kernel access, what happens around our cloud infra. If you see the EC2, EC2 has a full kernel access, and the TCP IP stack, in the full stack it has access. When you are having containers, we are going to have a shared kernel, and in that shared kernel we are going to have a namespaced approach. When we are going to have a lambda, it is not going to have any access, and the TCP IP stack in any access into kernel, and the TCP IP stack will be totally managed by AWS. And when we are doing things like S3 or DynamoDB, here for example S3 is totally object storage, so the kernel access is not at all intended there, and the TCP IP stack from the client only. While calling, we have some basic controls, but overall it is being totally controlled on the managed side only. So of course, like, understanding the operating system and the networking concepts is very important here. Now again, let's talk about some of the real life problems, what might happen from the cloud perspective. Okay, so you are building a microservice in your cloud, okay, and the HTTP connection. So what it is doing is it is creating a long-lived HTTP connections like the gRPC or the REST client. If for idle, if it is being kept idle for too long, we see that the firewall or the NATs or the NAT gateways, like, they start silently dropping the connection. So what we need to do is we need to increase the keep alive, because they are long lived connection and they can be kept idle for some time. So generally in the code, uh, we can handle using the socket HTTP handler. So socket HTTP handler is nothing but one of the low level access that C# provides you. So here, if you just this ping policy, if you increase a little bit and the ping timeout, then we are going to see that these problems are not happening. And also understand one thing: if suppose we are in Linux stack, we can do this kind of optimizations as well. So whenever we are seeing this connection timeout sort of a thing, uh, not only increasing the timeout from the like the code end, also if across all my operating system or all my web server, I can increase that by doing something like this sysctl keep alive time, the interval time, or the probe time. Okay, so this is one of the case. So let's take another case. Let's take another case like we are streaming large files over the internet, over the OSI stack rather, and we keep on hitting the throughput limits. Okay, so here what exactly happens is, so the default socket buffers may be too small for the high bandwidth and the high latency network. So the root cause is for this is the default socket buffer is too small. Okay, so what we can do over there is we can just um, make some changes into our in the Python code also, similar in the OS tuning. Like for example, if it is a Linux stack, we can always go to the socket and the send buffer and the receive buffer limits we can increase. Okay, so the resolution is in application code level or in OS Linux level, increase send and receive buffer limit. Understood? One more case. Okay, let's discuss one more case. So suppose we are building a custom protocol like game server, telemetry system, and we are not at all using HTTP. We can even build something around that. We can create our own accept, send, uh, the no wait, the things like what we discussed over there earlier. Uh, Earlier, like how we have created our JSON, how we are doing our serialization, how we are doing our select and epoll. We can completely create our own custom communication library. Okay, for example, it can be very simple. Like for example, if I take some example in Java, it can be as simple as this. Like I just create a server socket, because socket is the first thing that we are going to create on a given port, and then we create a client socket using that server socket, and then we create the get the output stream and the input stream, and we can also tweak what happens into the accept, what happens around the select and epoll. All these things we can tweak and create our own custom communication library. So here from OS side we can always like create from the OS side. Basically we have all this basic APIs exposed, which any of this programming library can use, and we can create our own custom communication library. Okay, um, let's discuss about one more thing. So suppose you have designed a set of microservices, okay, that communicates the rest over HTTPS, and you notice. Okay, let me just copy paste it for you. Okay, so what we have done is a microservices we have created that communicated via REST. Okay, and we see a high latency. And what we do is we at first try to see what is the request turnaround time. We see that it is less than 1 millisecond, right? And the CPU and the memory level also it is fine. And the connection life cycle from DNS to response, we need to start investigating now. So what will be our investigating point if we see that the RTT is very low and there is no issue on the CPU on the memory side? Okay, so first thing that we are going to check is about the DNS resolution. In DNS resolution, what are the things we are going to check? We are going to check if we are not able to cache the DNS properly. For that, in case like we are using AWS, our AWS X-ray traces will be good. So X-ray is one of the service that this kind of microservice architecture, in which hop the problem is, it helps us to resolve. And we can always see uh, whether those DNS caching is happening properly or not, and how much time it is taking for the DNS resolution. Okay, so the second thing I would say is setting the TCP connection setup. Okay, So what might be going wrong? Because I might not be reusing the connection, like one of the classic case that we just discussed, right? If we are not reusing the connection, like a very bad implementation it is, this we do some kind of a bad practice like that, then the TCP connection itself could be the problem, because the number of new connections per second that are being created, uh, it is it is simply exhausting the number of available ports. So what we have to check there is, like, there are the time wait counts, the connection polling properties, etc. Okay, then there comes like the TLS handshake. So what happens in the TLS handshake? The TLS setup is a CPU intensive and it adds some latency. Now also, like, if we just see the memory very diligently during TLS handshake, we will see that there is a sudden uh, spike in the CPU usage. Okay, so we have to just keep on checking our TLS logs as well, that what exactly is happening in terms of that transport layer security. Okay, after that, what if our application is under load, like something like a thread pool saturation might be happening. So for that, again, the matrices like the APM traces, the data dog, even the AWS X-ray, they give us the traces like APM trace or some other like signal effects traces. They give us all those details, whether the request queuing is taking a lot of time or not. Okay, and then after getting into all of this, if we don't find any problem in the network, then that means definitely the problem is like the application processing, because already checked we have already checked all these layers. If you see, one by one we are checking all the layer, like what is happening at the data link layer, what is happening at the transport security layer, and what is happening at the thread pool layer, and then we are coming into our application layer. So there again we are going to check our logs, and we are going to see like how much time exactly is being taken for this application processing. So I hope this part is clear to you. Um, when we are getting a microservice response delay, how we are going to approach this problem. Now, um, the last problem that I want to discuss is again a very interesting one. Suppose you are owning a deployment of Meta, okay, Meta or Facebook. Now, what you have seen over there is there are millions or billions of users are probably connected to your server, and you need to do a new deployment. So the moment a new deployment is being done, okay, so all the connections that are there, so suppose there is the point I'm trying to make is, if from the client we are connecting to the Meta server, so this is kind of a TCP connection that is being created, right? So once a TCP connection is established between the client and a target, that is primarily specified to a this target instance. Okay. So now for some reason I have to change this target. So suppose I am in some T2 micro in EC2. I need to change it to some other type. So what exactly will happen at that point of time is this connection will be terminated. The TCP connection that has been mentioned, it will be terminated. Now, as you can see, for this new deployment, if you are deploying, suppose in a new server, what exactly happen is there is a chance that all the users are getting logged out as, let me just, all the users are getting logged out as the TCP connection will drop on the deployment. Okay, but this is not an expected thing, and that doesn't even happen to us, right? So what exactly happens there is, so this user sessions in real life are stored in some kind of a database or some kind of a common layer like Redis or some a very fast access DB. Okay, and or in the client side cookies also. So these tokens are not exactly tied in this manner with the with directly with the target. What happens is when a new version is deployed, the session token is still valid, and when we are making that request by taking the um, by although the TCP connection might break, but because we are making the request uh, using this tokens like here the concepts like the JWT token and other things will come, which is not exactly in the scope, but still I'm covering because we need to take care of this use case. This JWT token will be there in the Redis, right? So what would happen is our instead of instead of putting everything here, it will go to our JWT token. It will take the JWT token, and from there it will go to the target, right? So uh, Facebook web servers are completely stateless, like they are not maintaining any state. All the states are being stored in some kind of a shared place, and when a new deployment happens, suppose from target, the target machine totally checks, only this connection breaks between that, like although the connection breaks, like if it is a TCP connection it will definitely break, but because our tokens and all the security information and the cookies are stored somewhere else, so the client able to make that connection again seamlessly. Now how exactly JWT works behind the scene, probably like that is bit of a backend concepts which will elongate the video like anything, but explore this kind of real life scenarios through which you will understand this kind of concept more. And that's the video, guys. Like this concludes the OS internal series, and in the next series will be on networking. See you in my next video. Till then, stay awesome.